Morning, folks. Just a little bit of update on what we're doing and where we are. The project is due on April 30th, so that's a week from today. Did I change it to what? To the 2nd. All right. The project is due on May 2nd. All right. Or did I say that there is no project? Yeah, that's what I said. No, all right. Now, the project's on May 2nd, and is that the last day of class? It is. Okay. So May 2nd, you have, what, a couple of weeks, I think. 2 weeks? A couple is 2. And we only have a few more class days. We will be meeting on Thursday. Let me pull up my calendar. So y'all know what's going on Thursday, right? What's happening in this room on Thursday? Oh, yeah, right. There is a test. I'm sorry. We are meeting on Thursday. And you'll come in. Dr. Lowe will be here, Glenn Lowe, and he'll be giving out the test. You'll have 30 minutes. And I sent y'all an email out yesterday. The whole thing with the calculators, like I'm okay loaning you calculators, but other faculty won't do that. So make sure that you bring a calculator. And if you need one, I'll loan you mine, and then you can just return it. Or you can get one from one of your classmates. And then also, I don't want them to have to deal with sort of shuffling calculators around. So if you don't bring a calculator, sorry, that's just sort of the problem that you'll face on your own. Is that clear? So bring a calculator to the test. And don't expect there to be calculators there. But if you need one, just come see me. I'll loan you one. So you'll have 30 minutes, be 15 questions, and it's only on Chapter 8. Only on Chapter 8. At the end of class, we'll have some time for your questions, and I'll sort of go over all the major topics, just sort of give you a 5-minute summary of what's on the test. And then if you have any questions or concerns about it, I'll address that then. All right? Is that clear? On Thursday will be the quiz. And then on Tuesday, we'll come back and we'll start on the next chapter. Today, I'll probably finish Chapter 10. And then on Tuesday, we'll start a little bit into light and optics, maybe get a little bit into lenses and mirrors. And those last 2 chapters will be on the final. They'll be 1/2 of the final. Isn't what I told you? It'd be half the final? Yeah, and then the other half will be cumulative. The cumulative part, if you're already studying for quizzes, the way you study for the cumulative part of the final will be to study the old quizzes. I'll take those questions. I'll change the numbers, might change the wording a little bit, sort of, but it'll still be the same idea. So if it's not on the quizzes, it won't be on the final. Is that clear? That's good. It should be good for you. Like if you're sort of lagging behind, it should be a place where you can push on through and get that A that you've been shooting for in this class. Okay? Because of that change, we won't have 5 quizzes. We'll only have 4. But I'll still drop that lowest quiz grade, as we discussed, so you really have 3 quizzes. Is that clear? Because I'll drop your lowest quiz grade, like we've discussed before. Have any questions? Concerns? Yeah, Jessica? You were just raising your hand? Oh, you're putting your jacket on. It's cold in here. I'm sorry. I can't do anything about it. Oh, look, my birthday's on the 27th. So if you want to get me a present, please do so. And then the last day of class is on the 8th, and our final in this class is on the 14th. It'll be in this room. It's at 8 a.m. That's right. That's scheduled by the university. It's on May 14th at 8 a.m. I don't have any control over that. If you didn't get your progress report for your project, then please drop by and get it. Remember, those are due on May 2nd. All right. So we've been sort of talking a little bit about electricity and magnetism. We talked about the ideas of potential, electric potential. Do y'all remember electric potential? What is that? Electric potential is something per something. Do y'all recall what that is? It's something per unit charge. It rhymes with synergy. Energy per unit charge. Thank you. So potential, which we measure in voltages, and that's like a 9-volt battery, is really just an amount of energy per unit charge. So if I have a 9-volt battery, it gives a certain amount of energy to an electron, but if I have a 12-volt battery, does it give more or less energy? to an electron. It gives more, right, because it has more energy per unit charge, that higher voltage. So we talked about potential and then also potential energy and how that's related, because potential energy is just, or potential rather, is potential energy or energy per unit charge. We talked about current, and current is how that's the flow of electricity. If I look in a wire, there's a certain number of electrons that pass in a given time, and that charge per unit time is the current, and we use that when we talk about electricity. Let's see. Those are sort of the big ideas. Oh, and then also Coulomb's law. Coulomb's law describes the force between charged particles. And you'll see all those things on the final exam for that chapter 10 portion. We also got a little bit into magnetic fields and magnets and how those work. We talked about permanent magnets and how we have these sort of imaginary things that we call magnetic domains. And magnetic domains are just collections of charges that their magnetic fields all align in a particular direction. And if you were to look at a permanent magnet, and this is just a sketch of a permanent magnet, like a bar magnet or whatever, the magnetic domains, which are represented by these little sections of the material. Again, these are just imaginary. We section off a little piece of it, and we say, what is the direction of the magnetic field for this little section? And these magnetic domains in a permanent magnet are all going to be lined up. Remember, magnets or magnetic fields are created by, intrinsically, by moving charges. And so everything has moving charges in it, like you do as well, because we're made up of atoms and molecules, and those have electrons that are zooming around all the time. And so everything has magnetic fields. It's just a matter of, do your magnetic domains line up? And so maybe some people, like their magnetic domains line up more than other people, so they have a more magnetic personality. Maybe that's true for some of y'all. But for most of us, our magnetic domains are just lined up randomly. All right? Let's see, there's a non-magnetic material. That's probably me. And then in nature, they're created in lava flows when these molten metals solidify in the Earth's magnetic field, and that causes them to align, the magnetic domains to align. So we talked about some of their properties. They have north and south poles. Opposite poles attract. Like poles repel. All right. Sort of on the last part of this, I want to look a little bit at the medical uses of magnetic fields. Just in the past 50 years or so, in the past few decades, the use of magnetic fields has become very important. So medical uses. Magnetic fields, I'll call them B fields, penetrate non-ferromagnetic materials. There's a little effect on the body. All right, what is a non-ferromagnetic material? Or first of all, what is a ferromagnetic material? You need to know this definition. Like you could just have a multiple choice question about it. What does ferromagnetic mean? It is able to be what? Not charged, but what? Iron, for example, is a ferromagnetic material. Ferro means ferrous, right? Copper, on the other hand, is not ferromagnetic. Wood is not ferromagnetic. Plastic is not rust. Okay, not rust. No. No, not has to do with conduction. Ferromagnetic. Right. So yeah, you're on the right track. So a ferromagnetic material can be magnetized, which is sort of what I heard you say. It can be magnetized. So like if I take a magnet and I hold it next to a paperclip, for example, which is largely made out of iron, if I hold it next to a paperclip, then I can attach other paperclips to that paperclip, right? because I've made a new magnet out of it. It's become magnetized. But ferromagnetic means that it's able to be magnetized. Ferromagnetic means it's able to be magnetized. Let me write that down. It means it's able to be magnetized. Like I said, iron is sort of the primary example of a ferromagnetic material. Ferro means ferrous, but copper, on the other hand, is not ferromagnetic. Able to be magnetized. So when I talk about magnetic fields penetrating non-ferromagnetic materials, what is that referring to? What is a non-ferromagnetic material that a magnetic field could penetrate? Right, your skin, your bone, your whole body. Like basically none of your body is ferromagnetic, but none of it is really able to be magnetized. So these magnetic fields, because you're not ferromagnetic, none of us are, then those magnetic fields can penetrate our body without doing any damage, without changing the body in any way, because we're not ferromagnetic. Right? So ferromagnetic means that you're able to be magnetized, and since our bodies are not ferromagnetic, these magnetic fields don't affect us. And so with that, there are a number of uses. Just for example, you can direct a catheter through the body. Without actually touching it, you can use a magnetic field that's external to the body to direct a catheter to wherever it is that you want it within the body. Magnetic fields are used to remove bits of iron from your eye. So whenever you have these ferromagnetic materials in the body, you can affect them without affecting the body. All right, so like if you get bits of iron in your eye, you can use a magnet to remove those. You can also use magnetic fields to detect iron in the body. Like, for example, you can use them to detect asbestos. Or if you're Magneto, you can use it. Y'all seen that movie with Magneto? Yeah, X-Men, yeah, where he gives the guy a bunch of iron pills. Maybe I should talk. It was kind of a gross scene. Never mind. All right, but you like X-Men? Really? Okay. It was kind of a gruesome scene, if I recall. So those are a few medical uses. Let me go to the next page. I'll show you some others. Within our nervous system, there are electric currents. To transmit information. So it's very much like an electrical circuit where you have charges flowing through wires, but instead of wires, it's through nerves. And you have these charges that are flowing through nerves, and they're using them to send electrical signals to the brain or to other parts of the body. So because you have these electrical currents, and electrical currents consist of moving charges, then they generate a magnetic field. So you can measure the magnetic field. Due to these currents or moving charges. All right. Some examples of this, you can use a magnetocardiogram. This measures the magnetic fields generated by the charges in the heart, magnetocardiogram. This is also called an MCG, and this is used to monitor the heart, the magnetic fields that are generated by these moving charges within the heart. And then a magnetoencephalogram also, for example. This is called an MEG. I don't have it written in my notes. I forgot to look it up. I think this has to do with the head, right? Yeah, so to monitor the electrical currents and hence the magnetic fields that are generated by the brain. Right, so this has to do with the brain. All right. There are other uses. We don't really use magnetic tapes anymore. They've been sort of put aside by optical media like DVDs and CDs. But your book actually talks about other magnetic tapes like the little floppy disk. You know what I'm talking about? Like the little plastic disc you put in your computer, or the big floppy disk, or audio cassette tapes or VHS tapes. All of those used magnetic fields. There were little bits of iron that were deposited onto plastic strips, and then you could change the magnetic field of those devices in order to transmit particular types of information. All right, but again, we don't really use that anymore. We just write that. So other uses, which are very 1990s, floppy disk, VHS tapes, cassette tapes. All right. All right. This is the end of chapter 10. And before we move on to the next chapter, I want to just go over chapter 8. That's going to be all of the quiz on Thursday will be on chapter 8. I'm just going to sort of review all the major topics. And then if you have questions about those things, I'll address those questions as well. We also have to do evals today, so I'll let y'all do those in about 30 minutes or so, and then we'll wrap it up. So chapter 8 was on sound. Give you the 5-minute version. We talked about restoring forces, and one particular restoring force is given by Hooke's law, and that is just F equals kx. If I have a spring, if that spring is, if it's stretched out from its equilibrium position, then there's a particular force that acts on it, F. This K value is called the spring constant, and it's determined experimentally. All this should be in your notes. We also talked about the motion of waves. So these restoring forces are important in that they create this sort of what we call harmonic motion, or this wave-like motion. Let's talk about the motion of waves. And if we were to graph a wave like this, you can graph it in a couple of different ways. I'm going to graph the displacement versus time. So I have the displacement versus time. This would be like, for example, I don't know, a guy moving up and down on a diving board was an example that we used in class, where he goes up and down, and this gives his up and down motion, and then this is a progression of time. Now, from a graph like this, and you will have a graph like this, you'll need to be able to pull particular bits of information from this that describe the wave. One bit of information that you'll need to know how to find is the period. The period is the time from peak to peak. You'll need to know the amplitude. The amplitude is from the origin axis, the x-axis, up to the maximum. So this is the amplitude of the motion. And then also from the period, you'll need to know how to find the frequency. And the frequency is just 1 over the period. You'll be given a graph, and you'll need to be able to find those things on that graph. We talked about 2 different types of waves. Transverse waves, that's like if you take a water hose and you go like this and it makes a wave. And then the other type of wave was called a longitudinal wave or a compressional wave. And sound is which of those? Transverse or compressional? Okay, I'm hearing both. Okay, a transverse wave is like a water wave. You have these up and down peaks, okay? And a compressional wave or a longitudinal wave is where you have compressions and then rarefications. Compressions, areas of low pressure and high pressure. Which is sound? Is it a transverse wave or a compressional wave? It's a compressional wave, yes. So where you have these areas of high pressure, area of low pressure, high pressure, low pressure. So sound is a compressional wave. And then other waves like mechanical waves are like a rope, for example, are longitudinal or transverse waves. We also talked about the velocity of a wave, and the velocity of the wave is related to the wavelength and the frequency in this way. If you ever forget this equation, which is on your equation sheet, so you shouldn't, but if you ever do, just look at the units. This is meters, and frequency is 1/seconds, and so it gives you meters per second. All right. Also talked about intensity. The intensity of a wave describes how much energy it carries, and the intensity is equal to the power over the area. All right, there are some particular attributes to that because it's based on the area, and the area is proportional to the distance squared. If I move twice as far away from an object, how much does the sound go down? By a factor of what? It goes down by a factor of 4. And you can see that if I look at my intensity, intensity is equal to the power over the area, which is 4 pi r squared. You don't need to know that the area is 4 pi r squared. That's the surface area of a sphere. But you do need to know that it's proportional to the radius squared. All right? And so if I double, for example, my radius, goodness bless you, I get 1/4 the intensity. So as you move away from an object that's creating sound, the intensity drops precipitously as an inverse square. So if I move twice as far away, it drops by a factor of 4. If I move 8 times away, it drops by a factor of 8 squared, or 64, 1/64. Okay? Those types of mathematical relationships are important. You'll need to know how to use the logarithm. I'm going to make it a little bit simpler than what we did in class. I'll show you. Remember we had this thing. Theta was 10 log of I over I naught. This gives the number of decibels for sound. It's based on a logarithmic scale. And remember, logs work like this. The log of 1, which is the log of 10 to the 0, is equal to what? It's equal to 0. So the log of 10 to the x is equal to x. You just take that exponent. So for example, the log of 10 is equal to 1, because that's like log of 10 to the 1. Log of 100, which is the log of 10 to the 2, is equal to 2. Log of 1,000 is 3. Log of 10,000 is 4, and on and on. You can do these in your calculator, and I'm okay with that. But the logarithms that you'll deal with are just like this, where you just take the exponent. Nothing more complicated than that. Okay? You will have to calculate the number of decibels. I'll give you an intensity right here, and you'll have to figure out what are the number of decibels that sound has based on the I naught value. That's the threshold of human hearing. That's the lowest sound that you can hear. I give you that value, of course. So say, for example, if I is, I don't know, 10 to the minus 8 watts per square meter, what is beta? What is the number of decibels? So it's going to be log of 10 log of 10 to the minus 8 over 10 to the minus 12. And so that's 10 log of 10 to the 4, just 10 times 4, which is 40. You had a homework problem identical to that. Okay? So you will have to do that. You can almost bet on it. And so an intensity of 10 to the minus 8 is equivalent to 40 decibels of sound. All right? What you won't have to do, and you did have to do this in the homework, but you're not going to have to do this on the quiz, is you're not going to have to work backwards. So I'm not going to give you this and ask for the intensity. That's a little more complicated with logarithms. I think y'all can do it, but we're not going to see it on the quiz. Is that clear? Okay. I think these logarithms are fairly straightforward, but if you have trouble with them, just come see me. Yeah, Danae? Okay, the 10 to the negative 12 is the threshold of human hearing. It's the lowest value that you can hear, the lowest sound that you can hear. It's given, it'll be given like in the problem. Okay, is that clear? That changes, by the way, for different people. So, and not that much, but different people have different thresholds. Yeah. Right, 10 to the negative 12. No, it's 10 to the negative 12. 10 to the negative 2 would be really, really loud. Yeah. Okay. All right. Almost done here, I think. Oh, and then we talked about some things, just sort of topics, the reflection and attenuation. That intensity is affected by reflection when it reflects off of surfaces, attenuation when it's muffled. Can you hear me? Can you hear me? Right, you can't hear me as now when it's muffled. And then also the non-uniformity of the source. That is the source creating a nice even tone, or is it just making crazy sounds? We talk about ultrasonic scanners and how they work. I'll leave you with your notes on that, but you want to read through those. And the book has nice sections on that as well. And then also superposition of waves. We had two different types of superposition. We had constructive, when the peaks add up. That's called constructive. And then we had destructive, when the peaks and the troughs don't add up. And if you add these together, you just get a no wave at all. This is destructive. And if you add this together, you get a wave that's much bigger. That's like the frozen planet thing that I showed you when you added these multiple waves together. Beats, when I put two things together, two sounds together, say 300 hertz and 305 hertz, I hear this wah, 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 wah. What is the frequency of those beats? If I have 300 and 305, what is it? It's 5. It's just the difference in the two frequencies, all right? I showed a figure of that in class, and we showed you some examples of it too. Like we have to calculate the frequency of beats. It's a pretty useful tool when you're trying to, like if you're a musician, to tune a guitar. That's what you're doing when you're tuning a guitar, is you're listening for the beats. And then resonance, Doppler effect, and sonic boom. Every object has a resonant frequency, and when you direct that frequency to the object, it causes it to vibrate. And that was that little wooden box that I passed around with the tuning fork on it. You ding it, and then the box sort of amplified that sound. So this room, for example, has a resonant frequency. Fortunately, we don't reach it, or it's probably actually pretty low. Like we don't speak at that frequency, but if we did, the whole room would vibrate. Remember I told y'all about my experiment in class in high school where we found the resonant frequency of the building? Yeah, I did. I'm not going to say it. It was pretty cool. And then the Doppler effect. You have some homework problems about it. Coming towards you, it's higher pitched. Coming away from you, it's lower pitched. And sonic booms, that occurs because of the superposition of waves. Right. That was I think that was more like a 10-minute version. Questions about sound for the test. I know it's been a while since we've done that, but how y'all feel about it? Any questions, I guess. No, don't be scared. Huh? Only on Chapter 8. There will be 15 questions. Don't be afraid. Never be afraid. No questions about it? Yeah, do your homework. Read through your notes. I think you'll be just fine. But make sure you can do all the homework problems, except for that one going from decibels to intensity. You're not going to have to do that on the test, but you will have to go from intensity to decibels. Is that clear? All right. And remember what did I say about calculators? Bring your own calculator, right, because Dr. Lowe won't have calculators. So, all right. And also, I doubt that he'll allow you to pass calculators back and forth. I know I do that, but I doubt that he will. All right. I have a little bit more time. I want to go into the next chapter just a bit. And then all right, let's do light. I think that so like light is kind of fun. We're going to look at two different properties of light, and then if we have time, we might get a little bit into optics using lenses and mirrors to do particular things, because that's really the application that you might be concerned with, using lenses in particular. There are a couple different properties of light: the reflection of light and the refraction of light. The reflection of light is fairly intuitive, I think, because we see it a lot. The reflection of light. Actually, somebody have a book? Somebody, can I see a book? Can I see your book, Jen? Mine? What chapter is this? Is 14. Yeah, this is going to be chapter 14. Sorry, I'm sort of going off the cuff right here. That's scary, isn't it? Yeah. Okay. So reflection and refraction. Okay. Thank you. All right. The reflection of light. When light is incident on a surface, so let's say that I have a reflective surface right here, and I have light that is incident on that surface, like this, it's going to reflect in such a way that this angle, which I'll call the incident angle, theta I, is equal to this angle, theta R. So the reflection of light is dictated by this, that theta I is equal to theta R. There's kind of an interesting historical progression with this. Don't write this down, but I think it's fairly interesting. Isaac Newton was one of the first people that studied this whole idea of reflection of light. Actually, people had studied the reflection of light for years before he had, because they had mirrored surfaces and they had light and they could observe the reflection of light. But when he looked at the reflection of light, he said that light was a particle, because particles follow this too, right? You ever bounce a ball on the ground? Or you play pool? They always follow this rule that the incident angle is equal to the reflected angle. And so Isaac Newton said then that light had to be this stream of particles. And we'll come up later where we actually find that other people have said that light is not a stream of particles, but that it's a transverse wave, like we talked about in the previous chapter. Not a compressional wave, but a transverse wave, where you have this varying energy per time. So the reflection of light is very much a demonstration of the particle-like nature of light. And Isaac Newton saw this fairly clearly. That's the reflection of light. And then there's another property of light called the refraction of light. The refraction of light is the bending of light. Because the light slows down. And the light travels at a different velocity in a medium. And this is observable. It's pretty easy to observe, actually. I mean, you could probably even put together a simple experiment to do this, where if I have light that's traveling along, I have this light ray that's traveling through space, and it has a particular speed. That speed is 3 times 10 to the 8th meters per second. So that's what, 300 million meters per second. And then when it enters a medium, say it enters, I don't know, glass, for example, when this light ray continues on, it travels with a different speed. For example, with glass, it would travel at about 2 times 10 to the 8th meters per second. So its velocity drops, or its speed drops by a full third. As I said, that's easily observable, and it's been known for a couple centuries, I guess. All right. So the refraction of light, I go down from here. Now this change in velocity is given by this. The velocity of light in a medium is equal to the speed of light divided by n, where n is called the index of refraction. And c is the speed of light. Right. N is measured experimentally, so you would measure the speed of light in a vacuum and then measure the speed of light in a material, and then you can determine what is the index of refraction. It's just determined experimentally. So for example, with glass, like in the previous page, it is found to have an index of refraction of 1.5. And so that's where I got that speed for glass, that V for glass is equal to C, which is 3 times 10 to the 8th meters per second, over the index of refraction for glass, which is 1.5, and so that's 2 times 10 to the 8th meters per second. So when light enters a medium, it slows down. Right? When light enters a medium, it slows down. Or if it goes from a medium to a vacuum, then it's going to speed up. Let me sort of write that in words. If n increases, if n goes up, then the velocity of light will go down. If n goes down, then the velocity of light will go up. Now, this causes some interesting things. Actually, I'll just do this and we'll wrap it up. If I get light that comes into a medium at an angle, say I have light that comes in at a particular angle, I'll call this theta I, and this is going to be air or a vacuum, and then this will be glass. So the speed of light here is going to be 3 times 10 to the 8th, and the speed of light here will be 2 times 10 to the 8th meters per second. When it enters this new medium, it's going to cause it to bend. So if I imagine these as a front of waves, which is really what I have, when I have light that's traveling through space, it's not just a single ray. There's actually a whole collection of rays that create this, what we call a wave front. So if I imagine these fronts of waves as they travel through space, some of those waves, when they enter the medium, are going to travel slower than some of the other waves. I like to think of this, and have you ever do marching band? This is the analogy that's always used for marching band. Have I ever done marching band? I played the tuba. What'd you play today? You played drums? Daniel? Clarinet? Really? What'd you play? Oh. Huh? Hey, me too. Yeah. So a marching band. So if you have a marching band that's traveling along where it has a good velocity, say on asphalt, for example, and then you have a drum major that's not very good, and they direct your band into, say, a muddy football field. What's going to happen to the band when they enter the muddy football field? They're going to slow down, right? But not all at the same time, because the corner of your marching band will slow down before the outside edge. So for example, if this is my marching band, this part of the Marching band will slow down before this part. So what's going to happen is this marching band, as it travels along here, is it going to move towards the normal, or is it going to move away from the normal? Is it going to move up or down? Y'all ever drive a twin rotor boat or a tank or a bulldozer on tracks? Ever do this? Yeah, so if you're in a tank or a bulldozer, if you make one side go faster than the other, then it turns, right? Like if I make this side go faster, it turns in this direction. Or if I make this side go faster, it turns in this direction. It's similar with a twin rotor boat, right? A twin prop boat, that I can make one propeller go faster and cause the boat to turn, basically on a dime more or less. And I can make it go the other way here. So a similar thing is happening here. I have one side that's going faster than the other, and it's going to cause the whole thing to shift around. I have this side which goes faster, and that's going to cause this whole deal to shift around. So when the light comes through the medium, it's going to look like this. Right? So I have this light traveling through, and then when it moves, it bends towards the normal. Now, the reverse is true also if it's moving from glass to air. So if I imagine my marching band now going from a muddy field in this direction, this side is going to go faster when it reaches the air, and so it's going to shift around in this direction. And so when it comes out, it's going to be traveling in this direction. So this is refraction. It's the bending of light, but it's just due to this difference in velocity. That light travels at a different speed when it enters a medium, and it causes light to bend. I have a little video I want to show you. The first, actually I have two I want to show you. The first is a video that a student of mine made a few years ago. This was Chris Cortez. I don't know if you know Chris, but he cut grass. Oh no! Don't tell me that. Sorry. Okay, maybe it's not going to work today. Well, I'll just show you. So we can see this bending of light in a lot of different ways, just sort of in the world around us. Today when you're at lunch, notice you really have to have a glass filled with water. And if you have a glass filled with, hello? Yeah, if you have a glass filled with water, and I put a straw into it, have you ever noticed what happens to the straw? It looks sort of separated, right, or bent. It sort of depends how you look at it. The straw usually looks like this to me, where one part of the straw looks disjointed from the other part of the straw. And that's because light, as it travels from the water medium to the air, actually bends, and it looks like it's coming from a different place than where it actually is. And then the straw that's in the air, you actually see its actual position. Whereas the straw that's in the water, you see just an image of it. A similar thing with fish, for example. Like say that you're standing here and, I don't know, you're bow fishing or whatever. That's a bow and arrow. And you have a lake here, and there's a fish underneath the water. All right? The light from this fish will travel out of the water, and then it's going to bend and come to your eye. And so it's going to look like the fish is actually coming from a place that it's not. And so if you're out bow fishing, then if you see a fish, you actually need to shoot below the fish in order to shoot the actual fish. I think that's probably a pretty good place to stop, but I still have a couple more things for you. First of all, let me finish handing out your progress reports. I think I got most everybody, but just raise your hand if you didn't get a progress report. Y'all just come on up if you didn't get it. Adams, is that right? Which one?
Piccolo.
Piccolo, okay. If you didn't get one, come on up. Oh, there you are. It's out of 20, yeah. Fish on, right? Gabriel? I don't think you did. I handed it out earlier. There you are. Anybody else not get your progress report? There weren't any issues with it. If there were issues, I emailed you, but most of them were just fine. So if you didn't get one, then please come get me. All right, guys. Next thing we're going to do are course evals. But let me do a few things up here because I have to go. I do need someone that's willing to do the course evals for me. Not everybody at once. Am I willing to do that, Rachel? All right. Just give me just a minute, Rachel. So I want to go over them. Sure.